All right, so get this. Today we're diving deep into antimatter. It might sound like something straight out of Star Trek, but it's a real thing.
Yeah, it really captures the imagination, doesn't it?
It does. And you know what's even cooler? You sent us a whole bunch of articles, research, and notes about it. I'm excited to unpack it all with you.
Well, I'm ready to jump in. I think what's so intriguing about antimatter is that it's like looking into a mirror universe, you know?
Whoa, a mirror universe.
Yeah. Like, imagine a world where instead of electrons, you have positrons. Instead of protons, you got antiprotons. It's particles, but with the opposite charge.
So instead of a regular electron with its negative charge, there's a positron with a positive charge. But it's still like the electron's twin.
Exactly. And the best part is, this isn't just some theoretical idea. Antimatter is a real thing, and it's got the potential to unlock some incredible secrets about the universe.
Okay, you've got me hooked.
Yeah.
But before we go too far, let's back up a bit. What exactly is antimatter? I mean, how would you explain it to someone who's hearing about it for the first time?
Okay, so think of it this way. Antimatter is like matter's identical twin, but with a twist. For every particle of matter, there is an antiparticle. Same mass, but like we said before, the opposite charge.
Okay, that makes sense. So if they're like two sides of the same coin, what happens if they meet?
Oh, it's not a gentle meeting. When matter and antimatter collide, they totally annihilate each other. Poof, gone.
Whoa, intense.
And all that mass, it turns into pure energy. That's where Einstein's famous E impepe comes in. It's the ultimate demonstration of mass and energy being the same thing, just in different forms.
Okay, wow. Annihilation. That sounds powerful.
Yeah.
Kind of scary. But this makes me think about something. Could we use antimatter as fuel, like we see in sci-fi movies?
It's a super cool idea. The energy in antimatter is off the charts, way denser than anything we know. In theory, even a tiny bit could power a spaceship across the galaxy. But there's a catch.
Yeah, I figured there had to be a catch.
Producing and storing antimatter. It's incredibly tough and crazy expensive. Right now, we can only make minuscule amounts of it, and keeping it from, well, annihilating is a huge challenge.
So no antimatter-powered spaceships cruising around just yet.
Not quite. One of the biggest problems is that antimatter just can't resist annihilating itself the moment it touches regular matter.
Ah, right, back to that.
To store it, we use these things called magnetic traps. They basically make the antimatter particles levitate in a vacuum using super strong magnetic fields. This keeps them from touching the container and going poof. But even these traps have limits. They can only hold a tiny amount for a short time.
So scaling that up to fuel a spaceship? Probably not happening anytime soon.
Yeah, we'd need a magnetic container so big and powerful it's beyond what we can do right now. But hey, even if those spaceships are far off, the possibilities are still pretty mind-blowing.
Totally. But it's not all about spaceships, right?
Yeah.
I remember reading something about antimatter being used in medicine, too.
Absolutely. You're thinking of PET scans, right?
Yeah, PET scans. That's pretty amazing, using antimatter to see inside the human body.
It really is. They inject a little bit of a radioactive substance that emits positrons into the body. And then those positrons bump into electrons in your body. Annihilation happens.
And then what, we glow in the dark?
Well, not quite. But the annihilation releases these things called gamma rays, and doctors use special detectors to track them. It's like creating a 3D map of what's going on inside you, which is super helpful for diagnosing all sorts of stuff.
That's wild. So we're using the energy from annihilation to see inside ourselves. But hold on, let's rewind a bit.
Yeah.
When did we first discover this whole antimatter thing? Wasn't there a big moment back in the 1930s?
You're right on the money. 1932, the year the positron, the antimatter twin of the electron, was discovered. It totally changed how we understand the universe. This physicist, Carl Anderson, was studying cosmic rays. You know, those high-energy particles that rain down on us from space?
Yeah, I've heard of them.
Well, he was using this device called a cloud chamber to see the paths of these charged particles, like watching tiny invisible fireworks. And what did he see? This particle that looked just like an electron, but curved the opposite way in a magnetic field.
So it meant it wasn't an electron, right?
Exactly. It meant it had to have a positive charge, the opposite of an electron. Boom! The first evidence of antimatter, confirming what Paul Dirac, another physicist, had predicted earlier. It was a huge moment.
A whole new world of physics opened up. Huh?
Yeah.
But this brings up a big question, right? If matter and antimatter were supposedly created equally in the Big Bang, why is there so much more matter than antimatter? Where did it all go?
Ah, the billion-dollar question. It's called the matter-antimatter asymmetry problem, and it's been bugging scientists for ages. Think about it. If the Big Bang made equal amounts of both, they should have just wiped each other out, leaving only energy. but that's not what happened. Somehow, matter won.
So are we basically living in a universe that shouldn't exist?
It kind of seems that way, right? But there are tons of scientists out there trying to figure out why. Some think there might be tiny differences in how matter and antimatter behave, like how they interact with the fundamental forces of the universe.
So maybe there are cracks in the laws of physics that we haven't found yet.
Maybe. Others think there might be undiscovered particles or forces out there that mess with matter and antimatter differently, causing this imbalance.
So there could be a whole hidden world of particles and forces we don't even know about.
That's what they're trying to find out. They're doing experiments at places like the Large Hadron Collider to study antimatter up close, looking for any little hint that could explain this cosmic puzzle.
That's incredible. Something so seemingly abstract as antimatter could be the key to understanding the whole universe. But it's not just about cosmology, right? I remember reading that studying antimatter has led to some pretty cool tech advancements, too.
You bet. Think about medical imaging, like the PE scans we talked about, or even more efficient nuclear reactors. Those have been influenced by antimatter research.
So while we're searching for the big answers about the universe, we're also finding ways to make things better here on Earth, too.
Exactly. It's like this. The more we learn about antimatter, the more we uncover about the universe, but also about how to use that knowledge in practical ways.
All right, so we've covered the basics of antimatter, its potential as fuel, and its role in medicine. Where do we go from here?
Well, there's still so much more to explore. Next up, we're going to zoom in on those positrons you mentioned earlier and how they act like messengers, carrying information about some of the most extreme events in the universe.
Positrons as cosmic messengers. Now that sounds fascinating. I can't wait to hear more. So positrons, right? These antimatter versions of electrons. You mentioned they act like messengers from these crazy events out in space. It's like they're telling us stories from across the universe.
Yeah, it's like they're carrying secret messages, whispering tales of cosmic explosions and black holes.
Okay, I'm all ears.
Yeah.
Let's start with supernovae, those giant star explosions. How do positrons tell us about those?
So picture a massive star, right? It runs out of fuel, collapses in on itself, and then boom, a supernova. It's brighter than a whole galaxy for a short time.
And these explosions create positrons.
They do. The explosion unleashes a crazy amount of energy, and some of that energy goes into creating positrons. These positrons get blasted out into space, carrying information about the supernova with them.
So it's like they're little pieces of the explosion carrying a message.
Exactly. By studying the energy of these positrons, we can figure out things like the temperature and density of the supernova. We can even learn about the magnetic fields that were there.
It's like we're piecing together a puzzle. But instead of pieces, we're using positrons.
I like that. It's like cosmic archaeology, using positrons to dig into the past.
But supernovae aren't the only things that make positrons, right? What about black holes? Those things are always fascinating and kind of scary at the same time.
Oh yeah, black holes definitely make positrons too. And it's one way we can learn about them, even though they're so hard to observe directly.
Because their gravity is so strong,
Yeah.
like not even light can escape.
Right, but as stuff falls into a black hole, it heats up like crazy and gives off all sorts of energy, including positrons.
And some of those positrons manage to escape the black hole's pull.
They do, and they carry clues about the black hole, like its size, how fast it's spinning, and even what it's gobbling up.
So we're basically using positrons to spy on black holes from a safe distance. Pretty clever.
Exactly. We can learn about these mysterious objects without getting too close.
Now, I remember you mentioned pulsars too, those spinning neutron stars. They make positrons as well, right?
They do, and they give us a glimpse into the crazy magnetic fields around these things. Pulsars are like cosmic lighthouses, beaming out radiation as they spin.
I remember reading about that. It's like they're sweeping the universe with these beams of light, right?
Yep, and those beams interact with the stuff around them, and bam, positrons.
And those positrons can tell us about the pulsar's magnetic field.
Exactly. They can tell us how strong it is, how fast the pulsar is spinning, and even what kind of stuff is around it.
It's amazing how each of these cosmic events has its own positron fingerprint, like a unique signature.
It's like they're speaking a different language, and we're learning to understand it.
Okay, so now I'm curious, how do we actually detect these positrons? I mean, they're coming from space, right? Do we just set up a giant net or something?
Not quite. It's actually quite tricky. Cosmic rays, which include positrons, are constantly hitting Earth, but our atmosphere mostly blocks them.
So we need to get above the atmosphere.
Exactly. We use high-altitude balloons or even satellites with special detectors to catch these particles before they get absorbed by the air.
So it's like sending our ears into space to listen for these positron whispers. What do those detectors look like?
Well, one type is a magnetic spectrometer. It uses magnetic fields to sort particles by their charge and momentum.
So it's like separating the good stuff from the bad stuff.
Kinda. By watching how a positron bends in the magnetic field, we can tell how much energy it has and where it came from.
So it's not just catching them. It's figuring out what their story is, where they've been.
That's a great way to put it. Each positron is like a tiny piece of a giant puzzle, helping us to understand the universe better.
And speaking of puzzles, earlier we talked about the possibility of antimatter galaxies. Whole galaxies made of antimatter. That's mind-blowing. How would we even know if they're out there?
That's the challenge, right? Antimatter galaxies would look pretty similar to regular galaxies, so we need to find other ways to spot them.
So no telltale signs that would scream, hey, I'm an antimatter galaxy.
Not visually, at least.
Yeah.
But there are some clues we could look for, and positrons are one of them.
Okay, kind of clues. If I were a positron detective, what would I be looking for?
Well, imagine finding a bunch of antihelium nuclei in cosmic rays. That would be pretty suspicious.
Antihelium, like the opposite of helium.
Exactly. A little bit of it can form naturally, but a lot of it. That could mean there's a big source of antimatter somewhere out there, like a whole galaxy.
So that's like finding a smoking gun, but instead of a gun, it's antihelium.
Exactly. And another clue would be how antimatter galaxies interact with regular ones. If they collide, it would be a huge explosion, releasing tons of energy as gamma rays.
So we'd be looking for these massive bursts of gamma rays as a sign of these cosmic crashes.
Exactly. And while we've seen some gamma ray bursts that could be from this, it's still tough to tell for sure.
It's like trying to solve a cosmic mystery with only a few clues.
That's what makes it so exciting. Even if we don't find whole antimatter galaxies, the search itself pushes us to develop better technology and understand the universe in new ways.
It's like every step we take brings us closer to understanding those big, mind-blowing questions about the universe.
Absolutely. It's about the journey as much as the destination, and this journey has been incredible.
It really has. But hey, we've been talking about the big cosmic stuff, the really far-out ideas. What about stuff here on Earth? Are there other ways that we're using antimatter in everyday life? I know we talked about PT scans in hospitals, but is there anything else?
Oh, definitely. The tech we've developed to study antimatter has found its way into all sorts of fields. Think materials, science, cancer treatment, even quantum computing.
Whoa, that's awesome. So it's not just about the big cosmic questions, it's about making things better here at home, too.
Right. For example, the traps we use to hold antimatter, they're being used to study ultra-cold atoms. This can lead to new materials with all sorts of cool properties.
Like antimatter research is a gift that keeps on giving.
That's a great way to put it. And the detectors we use to study positrons from space, they're helping doctors diagnose and treat diseases more effectively.
It's amazing how something that seemed so abstract at first can have such a direct impact on our lives.
I know, right? And there's even more. The way we produce and control antimatter. It's being used to explore new ways to fight cancer, like with antiproton therapy.
So even though it's this strange and mysterious thing, antimatter research is making our lives better in so many ways.
Exactly. It shows that even when we're driven by pure scientific curiosity, it can lead to real, practical benefits.
It's a reminder that exploring the universe isn't just about what's out there. It's about what we can bring back and use to improve things right here.
I totally agree. It's like a ripple effect, where scientific curiosity leads to unexpected and valuable results that can benefit all of us.
And who knows what amazing things are still waiting to be discovered. This is just the beginning of the antimatter story, right?
Oh, absolutely. There's so much more to learn. It's a field full of potential, both for understanding the universe and for making our lives better here on Earth.
Okay, well, as much as I want to keep talking about this all day, I think we need to take a little break.
Sounds good to me.
But don't worry, we'll be back soon to wrap up this awesome deep dive into the world of antimatter. And we're back. This deep dive into antimatter has been one wild ride. From the basics to spaceships, we've covered a lot of ground.
It's amazing how something that sounds so sci-fi is actually so fundamental to how we understand the universe, isn't it?
It really is. But before we wrap things up, there's something I've been thinking about. We've talked about the mysteries of antimatter, its potential as fuel, even its use in medicine. But why does it all matter? What's the real-world significance for us?
Ah, that's the question, isn't it? It's easy to get lost in the cool sci-fi aspects of antimatter, but it's so much deeper than that.
Right, like why should we care about something that seems so abstract?
Well, studying antimatter pushes us to confront some of the biggest mysteries of existence, like why are we here? What is reality really made of? These are questions humans have been asking forever, and antimatter gives us new ways to explore them.
It's like antimatter is holding up a mirror to the universe and saying, hey, look closer. There's more to this than you think.
Exactly. It challenges our understanding of what's possible and forces us to rethink our place in the cosmos. And honestly, I think that's one of the most valuable things about science, that sense of awe and wonder it inspires.
I totally agree. It's like the more we learn about antimatter, the more we realize we don't know, and that's exciting.
Right. It fuels our curiosity and drives us to keep exploring. That's what makes us human, this constant desire to understand the world around us. And antimatter, with all its strangeness and mystery, is like the ultimate challenge for that curiosity.
It's like a cosmic detective story, trying to piece together the clues and unravel the secrets of the universe.
And the best part is, the story is still being written. Who knows what incredible discoveries are waiting for us just around the corner? Maybe we'll find new ways to use antimatter that we can't even imagine right now.
Or maybe we'll finally solve that big puzzle of why there's so much more matter than antimatter.
Maybe we'll even stumble upon something that completely changes our understanding of the universe, something we never even thought to ask.
It's that sense of the unknown, that possibility of uncovering something truly groundbreaking that makes this whole field so captivating.
It's a reminder that there's always more to learn, more to explore. The universe is full of mysteries, and it's up to us to go out there and unravel them.
And on that note of cosmic mystery and the thrill of discovery, I think it's time to wrap up our deep dive into the world of antimatter.
It's been a fascinating journey, hasn't it?
It really has. And a huge thanks to you for guiding us through it. I hope our listeners have enjoyed exploring this fascinating realm with us.
The pleasure was all mine. It's always exciting to share these ideas with people who are curious about the universe.
And for all those listening, remember, keep looking up at the stars, keep asking those big questions, and never stop exploring the wonders of the universe. We'll catch you next time on our next deep dive into the world of science.